So let's get started on this thing. I'm going to draw a picture, not that you have to, but 4 over 3x squared should kind of look like, have this asymptote at 0 and should kind of do this on this side. And I won't worry about the other side because we only care about from 1 to 4. So that's the area in there that we're looking for. Which means I'm setting up this integral from 1 to 4. If I have to find the antiderivative of this, I'm going to go ahead and rewrite this to say 4/3 of x to the -2. You don't have to do that. It's just easier for me to see what to do. I don't even need a u substitution or anything. We're just going to add 1 to that exponent. So I'd have x to the -1, divide by the new exponent is going to make the whole thing negative. And I'm going from 1 to 4. So that x to the -1, I'm going to think about as being in the denominator. So I think I'm going to have -4 over 3 times 4 minus -4 over 3 times 1. That'll my, so 4s will cancel out. I've got -1/3 plus 4/3. Already have common denominator, 3/3, also known as 1. Yay. So secretly, what I actually just asked you to do was to show that P of x equal to 4 over 3x squared is a probability density function on 1 to 4. Up until this point, in terms of probability stuff, we've been talking about discrete things, which just means I can count it. That there are fixed values that it has, and I can count them. So if you think about flipping coins, it can only take on heads or tails. And if I do it 6 times, it can't land heads 3.2 times. But a lot of what we deal with in probability actually ends up being continuous. And for me, one of the clearest examples of this is anytime we're thinking about time. So maybe this represents the probability that I'm going to spend 1 to 4 minutes waiting for the bus to show up. So this function represents, if I tell you how long I've been waiting for the bus, this would be like the probability that I would be stuck waiting that long. Maybe that was a weird, I was trying to make this fit something in real life. I didn't do such a great job. That's okay. In terms of things that we already know about probability, from those discrete counting problems, I know that all of my probabilities always have to add up to, right. So when we switch over to thinking about continuous probabilities, they also have to add up to 1. But rather than having, if we think about, let's go back to a discrete example and thinking about flipping 3 coins. And x is the number of tails. Well, I could think about graphing that as well, where my x values were 0, 1, 2, or 3. And each of these probabilities comes from, we did this before, so I'm just going to recreate the chart super quick. But 0, 1, 2, 3. This is 1/8, 3/8, 3/8, and 1/8. So I could have this graph that looked like this. Scoot it up a little bit. So I could have a graph that looked like this because we took on only the values of 0, 1, 2, or 3. And the area under the graph could still represent those probabilities. So if I wanted the probability that X was between 0 and 1, and I'm including the 0 and the 1, well, thinking about the graph, I can think about this area plus this area, or thinking about the numbers, I can think about the 1/8 plus a 3/8. What's happening when we switch this to being continuous is rather than having this specific set of numbers that it can take on, we have a situation where X can take on any value between, in this case, 1 and 4. The idea is still the same, that if I want to find for my continuous function up here, where P of X was 4 over 3x squared on 1 to 4, if I wanted to find the probability that X is between 1 and 2, rather than having some graph and being able to find the area by like using actual rectangles, I'm going to use some actual calculus and integrate this thing from 1 to 2. That's kind of our basic idea. When we make this switch to continuous probability distribution functions. So there are several things that we're going to be asked to do. So for the discrete probability distribution ones, what were some of the questions? What were some of the things we had to calculate for discrete? Like on the homework and stuff, what were things we were asked to do? The mean, yep. Standard deviation. And the mean is really the same as the expected value. And the variance, oops, I'm having trouble spelling today. That's a C. The variance. Anything else we were asked to do? I would say we were sometimes asked to do things like find the probability of X given a specific value of X. And we're going to do all of those same things for continuous distribution functions. And most of our equations haven't changed much. They just look a little bit different because instead of adding things up with a summation, we're making this calculus style and adding things up with an integral. So let's get another example of that. I meant to print things, but I didn't, so gotta cheat and look over here. So, sure. Oh, request to go back really quick and look at the bottom. Yes, for sure. And I've got our next good function here. Won't be too bad. Okay. So one of the fairly common things that we end up having to do is to either check that something is a probability density function or find a constant to make something a probability density function. And by the way, we often abbreviate probability density function as PDF, not to be confused with a portable document format. So if I need to find a value that makes this a probability density function, the biggest thing to remember is all the probabilities have to add up to 1. So when we're asked to either show that it's a PDF or find a constant to make it a PDF, what we're saying is that when we add up all the probabilities, but we're going to do that calculus style with an integral, when we add up all of these probabilities on the interval that they've given us, we have to get a value of 1. Again, just for practice, because I know y'all have a final. I'm going to let you do the integration, but I am going to say that K is a constant. And since this is a constant, I'm going to pull it out in front of my integral. And then I'm going to let you all do that integration. There's a question in the chat. The final is cumulative, but I would say you might expect some problems like this, where I'm kind of testing you on the new stuff, but in order to get through it, I can write a probability density function that requires you to use different techniques of integration. And I can also write a probability density function that goes from 0 to infinity, which would force you to do an improper integral. So I think there are ways to sort of to test on the new stuff conceptually, but force you to practice the old stuff to actually mechanically do the problems. So if I were guessing, that's what I think is going to happen on the final. What'd you get for K? Oh, you didn't do the K part. You did the other part. Okay. But you plugged in the 0 and 1. You distributed stuff out. That's what I was going to do. I was going to distribute to integrate.
I distributed and then I integrated.
Then go ahead and evaluate at the 1 and 0 then.
You can evaluate it without K.
Well, you can. You'll just have K floating around out in the front. There's a question in the chat. I do believe Friday's lecture has been uploaded. Yes. I didn't watch it, but I do believe it's been uploaded. Yeah, so if you got the integration part, just leave the K out here. I think I'm getting 1/2 x squared minus 1/3 x cubed. Does that look right to anybody else?
Yeah.
Got an impossible answer. That's really unfortunate. Maybe I can help. Is it a fractions problem?
No, I got K times 0 equals 1.
I think we're not going to get 0. So if I plug in the 1, I'm going to have 1/2 minus 1/3. And when I plug in 0, I'm going to have 0 minus 0. But when we plug in 1, I think we should definitely have 1/2 minus 1/3.
Where's the 1?
So when I distribute the x out, I have the integral from 0 to 1 of x minus x squared. So I add 1 to the exponent, divide by the new exponent. That's where my 1/2 and 1/3 came from. So now 1/2 minus 1/3, I get a common denominator of 6. That would be 3/6 minus 2/6. So I think I get 1/6. And I am looking at K times 1/6. And the whole point was that we needed this thing to be equal to 1. And if I require that to be equal to 1, it means that K has to be 6. So my PDF, or my probability density function, should look like f of x is equal to 6 times x times 1 minus x on 0 to 1. I said all those things that we could do discrete, we can also do for continuous functions. So let's talk next about that mean or the expected value. Expected value for those discrete functions looked like the sum of x times the probability of x. And the only difference when we switch to continuous is that expected value piece. We're going to add them up calculus style, which means we're taking an integral, but we still have x times, and then our probability density function is what replaces our p of x in the equation. So we'd have x times our probability density function, or if we were going to do it for this specific problem, I know that we could find our expected value by looking at the integral from 0 to 1 of x times 6x times 1 minus x dx. I do want to actually calculate this. Are we doing it together, or did you want to practice more integration on your own? I'm good either way. Together. I got some votes for together. Let's do it. So if we're going to do this together, I'm going to take that 6 and put it out in front of my integral. That's going to leave me with, sorry, let's put this up a little bit. That's going to leave me with x times x, or x squared, to distribute in. So when I distribute that in, I'm going to have x squared minus x cubed dx. When we talked about discrete, I mentioned that our expected value should always be something kind of within that range of values. So the same thing's going to happen here. I'm expecting to get a number between 0 and 1. If we don't, something went wrong. So let's hope we get a number between 0 and 1, because that's kind of like our range of values that we've got. So if I integrate this, just leave my 6 out there for a second. Looking at 1/3 x to the 3rd minus 1/4 x to the 4th from 0 to 1. When I plug in 1, I'll have 1/3 minus 1/4. I'm going to leave off the subtracting 0 if that's okay with everybody. We can either combine the fractions first or distribute the 6 in, which would be my vote. So the fractions look a little nicer. So if I distribute the 6 in, I'm going to have 6/3 or 2 minus 6/4. But 6/4, those are both divisits, so that's minus the 3/2. 2 minus 3/2 looks like 1/2 to me. So we got a number that is between 0 and 1. It's looking great. There's our expected value. If we can do expected value, we can do the variance also. Good times. let's talk about variance for a second. Did any of you take stats? Has anyone taken a stats class in a previous life? Okay. If you did, there are two common formulas for variance. One works really well for discrete and one works a little bit better for continuous. And luckily our book, when we switch to continuous, the book shows, totally go back for a second. And try to get this to be in focus. That'll work. Okay. It's not too bad. So I want to show you all where both formulas come from and kind of like how they match up. Don't flip back in your notes or anything, but does anyone happen to remember the formula for variance for a discrete function? You can say no. Yeah, we've got to subtract the mean or the expected value. So we take each of our x values, we subtract the mean. By the way, I'm using mu for mean because that's the one that our book uses. This thing we've got to square and then multiply by the probability. And we add that up we add that up summation style. When we switch over to continuous, we're going to be taking the integral. Now, if I have x minus mu whole thing squared times our probability of x dx, what I'm actually going to do is FOIL this out. So I'm going to treat that as an x minus mu times another x minus mu, so that I get x squared minus x mu plus mu squared, or x squared minus 2x mu plus mu squared. So I'm going to replace that in my integral here, so that I've got x squared minus 2x mu plus mu squared times p of x dx. And then I'm going to distribute my p of x through this. So I've got x squared p of x dx minus 2x mu p of x dx plus mu squared p of x dx. Now, the interesting thing here is that some of these things are constants, right? Like in the previous problem, we found what the value of mu was. And once we've evaluated the integral and figured out what mu is, it's a constant. So in terms of these formulas, I can pull it out in front of the integrals. And that's what I'm going to do. So this first one, not much I can do here. None of that stuff for constants, but here I can pull out the 2 and the mu. And then in here, I would have x p of x dx. And here I can pull the mu squared out. One of those three integrals we already know the value of for any probability density function.
Wouldn't that be the second one? Did we just find that?
We did just find that. So this thing we just found, that is also known as the expected value. And the symbol that our book uses for expected value, specifically for continuous distributions, is mu. We also know the value of one of those other two integrals. Totally. This one always, always, always has to be 1 for any probability density function. So when we switch over to continuous distributions, turns out that it's usually easier to integrate to find the variance by getting ourselves down to just one integral and then subtracting off the constant of mu squared. Because we've got a -2 mu squared plus a mu squared. The most common thing that I will just caution everybody about is if this part requires integration. This is literally subtracting a constant after you're done. It's not part of the integration because it already came from knowing what the values of those other integrals were. Let's apply this to the function we've got going. So looping back around, our density function is 6x times 1 minus x on 0 to 1. So if I wanted to find the variance of x, this would look like the integral of x squared times 6x 1 minus x on 0 to 1 minus what we just found for mu, which was 1/2 squared. A little bit tedious, but not terrible, right? Because the only thing we've got to do now is take another integral. Should we actually take another integral? Or call it? Get another example going. So high energy on this Monday after Thanksgiving. I know, me too. I'm like, probably ready for a nap. But I'm gonna do some calculus instead. Let's integrate this thing. Good times. I'm gonna pop that 6 out in front. Now I've got an x squared times another x. So that'll be an x cubed to distribute out. So I'm looking at an x cubed minus an x to the 4th dx. Whole thing, don't forget back here, we're going to subtract 1/4 when we're done with the integration. Add 1 to the exponent, divide by the new exponent. Add 1 to the exponent, divide by the new exponent. We're going from 0 to 1. We got this. That's looking like a 1/4 minus a 1/5 minus another 1/4 over there. I don't know, common denominator now, common denominator later. I'm going now. Because distributing the 6 in doesn't help as much as it did last time. So I'm going to multiply this by 5/5 and this by 4/4. So I'll have 5/20 minus 4/20. So that's a 1/20 and then minus 1/4. The 1/2 squared came from the work we did on the previous page. So the mu is equal to 1/2 for this function. It's not always a 1/2 squared. It just happens to be 1/2 for this problem. So let's see, 6/20. I reduce that a little bit. I can make that 3/10 minus 1/4. Whatever, it's good enough. Let's just quit there. Oh, it's not terrible. I'll finish it. Okay, we can get a common denominator. I'm going to be lazy. 20 works, right? So 2/2, 5/5. That's a 6/20 minus 5/20. Oh, hey, cool. 1/20. So that's my variance. And just like with our discrete, if I wanted to turn that into the standard deviation, I'll just pop it inside of a square root. Time for another one? What do we think? Trying to keep them like not crazy messy because they can get crazy messy. But oh, there is one other thing that we could do, which is to find the median. Okay, I will give us one that leads to integration by parts for sure. Yeah, let's do it. So, okay. This one will definitely lead us to integration by parts. So my function here is going to be one half e to the negative t over 2 on 0 to infinity. And what I want to do first is to show that this is a probability density function. So let's show that this is a PDF. Then calculate the mean. Okay, we're going to get to practice all kinds of stuff here. So let's start with showing that it is a probability density function. To show that it's a probability density function, I need the integral from 0 to infinity of 1/2 e to the negative t over 2 dt. I need to show that that is equal to 1. Do you all, we got time. Do you all want to try this on your own for a couple minutes? Good practice as we're walking into the final. Give it a shot. If you're feeling really, really, really stuck, I'm happy to give hints. But give this a try on your own. If you don't like the 0 to infinity, ignore it for a minute. It is a negative. It kind of got smeary, huh? And I will say, so this one should not require integration by parts. It will when we calculate the mean, but at this step, it should just be a U substitution that you need. The next step will need an integration by parts. So here's my hint, if you want one.
E to a negative goes to 0, right?
Yes, e to the negative infinity goes to 0. But e to the 0 does not go to 0, which is what I think is going to save us. I think it's going to work.
It's gone to 0.
You think it's going to 0?
It's negative infinity divided by 2. Infinity divided by 2 is still infinity, so it's still e to negative infinity.
Right, but e to the 0 goes to 1. You know, on a lot of integrals, when you have 0, like when you plug in the 0, it goes away. Got to be careful with e. So if I rewrite this, or do y'all want more time? I can give people more time. It should converge. I'm hoping it converges to 1. Let's find out. So I'm looking for the limit as b approaches infinity, 0 to b. And I'm going to go ahead and make my u sub. So I'm just going to call this t equals 0 and t equals b so that I can do my u sub. I'm going to need that negative. The 1/2 and the dt are taken care of. So I'll just have negative e to the negative u du. Because that negative du is the 1/2 dt. So together that's negative du.
Where did you get the negative u?
Well, oh, no, you're right. It's a positive u. We'll just do that. You're right. Because I took the negative as part of my u. Yep, absolutely. Thank you. So when I integrate this, put this up a little bit. When I integrate this, I'm just going to end up with the same negative e to the u. But we're going from t equals 0 to t equals b. So I'm going to go ahead and plug back in to have negative e to the negative 1/2 t from 0 to b. Or negative e to the negative 1/2 b minus negative e to the 0. Well, this first part in terms of the limit, when I plug in infinity, infinity times 1/2 is still infinity, but then it's negative. And so e to the negative infinity goes to 0. Minus and minus makes that plus. So it is, in fact, a probability density function. Yay, we win. Now we're going to calculate the mean. One of the things just to be careful about, and I only did this because the book kind of changes up the variables sometimes. So we're finding that mean or mu or the expected value, whatever you want to call it. It goes with whatever variable we have in the problem. So I've been writing it as expected value of x, but x isn't really our variable in the problem, t is. So when we write this, we would have the integral of t times our function. 1/2 e to the negative t over 2 dt from 0 to infinity. This one, if we're going to calculate it, should we do it? Should we do our mean? We got about 5 minutes left. I think I'm just going to go for it. So if I'm going to find the mean here, I can definitely pull the 1/2 out. I'm going to ignore the limits for a minute because I don't want to get lost in the limits while I'm doing the integral. we're gonna need to integrate 1/2 t e to the negative t over 2 dt. And this does require integration by parts. Whether you put the 1/2 inside or you pull it out, doesn't matter. I happen to pull it out. But this thing definitely requires integration by parts. Because if I try for that u substitution, I have this t left over. Because I've got that t left over, I'm going to switch gears, think integration by parts. I've got a mixture of algebra and exponentials. I know that algebra comes first in the word late. So I would have my u equal to t and my dv be everything else. Now, I put this 1/2 out in front, but then I just realized that we literally just did this integral with the 1/2 in there. So I might as well leave the 1/2 with it because we already know what the answer is. Right, so if my dv is 1/2 e to the negative t over 2, we just integrated that and got negative e to the negative 1/2 t. Less work, because we already did it. And du would just be dt. Writing that in my ultraviolet voodoo, u times v would be negative t e to the negative 1/2 t minus the integral of ultraviolet voodoo. So I need negative e to the negative 1/2 t dt. The minus and minus is going to make that a plus. So I've got negative t e to the negative 1/2 t plus the integral of e to the negative 1/2 t dt. To integrate this, I'm thinking about a u substitution. I come off to the side over here, and u is negative 1/2 t, then du is negative 1/2 dt. But this time I don't have a 1/2. So my dt would have to just be negative 2 du. This piece we're leaving alone. Negative t e to the negative 1/2 t. This piece we're doing our u sub on, and that dt is getting replaced with negative 2 e to the u du. That thing I can integrate. Negative t e to the negative 1/2 t minus 2. Integral of e to the u is just e to the u. So I'll have e to the negative 1/2 t. And that whole thing I'm evaluating from 0 to b, ran out of space with a limit as b approaches infinity. Okay, I'm gonna flip the page and try really hard to not make a mistake writing it on the next page. So we've got the limit as b approaches infinity of negative t e to the negative 1/2 t minus 2e to the negative 1/2 t from 0 to b. Woo! We're like doing all the things in one problem. Negative b over e to the 1/2 b minus 2 over e to the negative 1/2 b minus 0 times e to the 0 minus 2 times e to the 0. When I plug in infinity here, yep. Yep, you're right. Positive, positive. Good call. It's not erasing well. I'll just make it a plus. Okay. So now when I plug in infinity, I have gotten myself into trouble. This limit right here is discussed in the book, but essentially e to the infinity is a way bigger infinity than just the regular infinity that's on top. This thing goes to 0, just like this one does. Over here, I'd have 0 times 1 and 2 times 1. So when you do it all out, we get 2. All that work just for an answer of 2. So that's our mean.